This is Kevin Cole at the University of Nebraska. The topic is thermodynamics, and the example is a heat exchanger for an automobile. In this example, we have a heat exchanger, and we've got water coming in at 205 Fahrenheit at a given flow rate, and it's coming out at 165 Fahrenheit. So that determines the amount of heat we need to remove from the automobile. And the water is being cooled by air entering at 40 Fahrenheit and 1,000 cubic feet per minute. And we do not know the exit temperature, and we do not know the mass flow of the air. So we're going to first find the mass flow of the air, and then we can find the outlet temperature of the air. We've got some assumptions. It's a heat exchanger. A steady is a common assumption for heat exchangers. We're going to take the pressure to be about 1 atmosphere. Certainly the air is at 1 atmosphere. Common heat exchanger assumption is pressure equals constant. We have no information on kinetic energy and potential energy, and they're usually neglected for heat exchangers because heat is the important interaction. We're going to neglect the heat loss to the surroundings. That is to say, our system is going to be the heat exchanger. We're interested in exchange between the fluids, but not outside the device. All right, on mass flow of the air, the information we have is that mass flow is area velocity divided by specific volume, and we don't have specific volume, but we can get that from the gas law. So air at 1 atmosphere applies to the gas law. Let's recast the gas law and solve for little v. That's going to be RT divided by pressure. Let's compute that. We've got some work to do. This specific gas constant is going to come from the universal gas constant. In English units, the universal gas constant is 1545 foot-pounds force per pound mole per Rankine. I'm going to convert that to the specific gas constant by dividing by the molecular weight of air, 28.97 pound mass per pound mole. That takes care of R. The temperature is 40, but I'm going to add 460 to make this degrees Rankine. And then finally I'm going to divide by the pressure. 1 atmosphere in English units is 14.7 pound force per square inch. And I need to convert inches to feet. There are 144 square inches in a square foot. If I crunch all of that, I get that little v is going to be 12.59 cubic foot per pound mass. And then I can take the mass flow to be a area times velocity times little v. But I don't know area nor velocity, but together that's the volume flow rate. So that's our 1,000. So we've got 1,000 cubic feet per minute divided by the specific volume that we computed, 12.59 cubic feet per pound. And when I crunch that, I get 79.4 pound mass per minute. Now we aren't told what the units are. Units are needed, so that's responsive. We're done with part A. We have the mass flow rate of the air. Okay, we need that to work on part B. The energy balance here for an open system takes this form. All we have left is mass flow rate and enthalpy. So the sum of the inlet mass flow rates times each of the inlet enthalpies is equal to the sum of the exit mass flow rates times each of the exit enthalpies. In this case, we have coming in, state 3 for the air is m dot air H3. Coming in for the water is m dot water H1. Coming out for the air is m dot air H4, and coming out for the water is m dot water H2. Now, another way to write this and think about this, is to rearrange it and put all the water terms on one side. So here is m dot water times H1 minus H2. That's the heat leaving the water. And that's the same as m dot air times H4 minus H3. That's the heat entering the air. So sometimes this is a useful way to think about heat exchangers. Now we're going to use, what I want to do for this problem, I want to use delta H to be Cp times a delta T for each side. We can do this because on the air side we have an ideal gas. And we can do this on the water side because that's an incompressible substance. Or in this case, an incompressible fluid. So same equation, different reasons for each side of the heat exchanger. So I want to rewrite this expression in terms of m dot and C sub p. It's going to take this form. M dot times C sub p for the water times T1 minus T2. That's going to be equal to m dot times C sub p for the air, and that's going to be times T4 minus T3. And then we're looking for the exit flow of the water. That is T4. So I'm a guy that likes to do algebra. So here's what the algebraic solution looks like. T4 is going to be T3 plus a ratio here of m dot C sub p for the water upstairs, m dot times C sub p for the air downstairs, times T1 minus T2. Now we can solve this if we can find the C sub p values, because we have the mass flow rates. The only thing we're missing now are the C sub p values. Okay, for air, the value that we know is 40 Fahrenheit. We need a table for that. Let's go find a table for air values. Here we have ideal gas specific heats in English units. Here's C sub p, here's air. We're looking for 40 Fahrenheit, there it is. The value that we need is 0.240 BTUs per pound per Rankine. So let me transfer that back. We've got from table A20E in this case, from a particular book, we found Cp for the air at 40 Fahrenheit to be 0.24, and the units were BTUs per pound mass per Rankine. All right, for the water, we have two temperatures. I'm going to find average temperature, T bar. The inlet was 205. The outlet is 165. So the average of those two is 185 F, and that's where I want to go to find the specific heat. It turns out that my table is in Rankine, so I'm going to add 460 to get 645 Rankine. So let me go find a table for water values. Here we are. Selected values of solids and liquids, C sub p, specific heat here in English units. I've got water down here. The 645 that I need is going to be in between 630 and 675 on this table, so the value for C sub p is going to fall between 1.002 and 1.008. You can check my interpolation. When I interpolated this, I found that C sub p for the water was 1.004 BTUs per pound mass per Rankine. That's a 4. All right, finally we can compute our temperature now. We've been given these values. Let me scroll up a little bit. We've got T4 is going to be T3, which is 40 Fahrenheit, plus m dot for the water is 15. That's in pound mass per minute. C sub p for the water is 1.004. Now, actually, the units of C sub p are going to cancel. The mass flow rate for the air is 79.4 and that's in pound mass per minute. And the C sub P is 0.24. The temperature difference is T1 minus T2 for the water is 205 Fahrenheit minus 165 Fahrenheit. And that's going to give me, I'll write it this way, I'll write the 40 plus 31.6 is what this stuff crunches to. And so the sum there is 71.6 Fahrenheit. That's my exit temperature. The increase in air temperature is about 30 degrees. All right, the final thing I want to do, I want to quickly check, a little space down here, I want to check if C sub P for the air is okay at T bar. Now that we know the final temperature, we can find T bar. It's going to be 40 plus 71.6 divided by 2. T bar is 56F. Go back to the table. And the table says, whoops, let's try that again. Go back to the table. The table says air at, I'm looking for the T bar is 56. It'd be in between 40 and 100. The C sub P value remains 0.24. So my conclusion is, coming back here, is that the C sub P value is the same. C sub P at T bar is the same value. No change required. Now if C sub P had come out to be different, we could have gone around again and iterated once to correct the C sub P. All right, let's recap. We're looking at a heat exchanger problem, and we had no loss to the surroundings, so the Q was 0. We had there was no shaft here, so the work was 0. So then our heat exchange, our energy balance was just mass flows and specific heats. We used the gas law. Just when we have air, that's fine. Pull in the gas law whenever you need to. We used, rather than H's, I decided to use C sub P times delta T, and we can do that on the gas side because it's an ideal gas. That's an appropriate expression for ideal gas. And that's also appropriate for an incompressible fluid. That's the way we treated the water. We had to use English units for this problem, of course, and we used an average value for finding the C sub P for the water. We didn't do that for the air. We only had one value for 40 Fahrenheit, but at the end we went back and we checked. And if you check to make sure that your C sub P values agree with the average temperature value, then all will be well.